this module, we will be talking about the concept of angular momentum in quantum mechanics. Angular momentum is an old concept. All of you are aware of that. Whenever there is a circular motion, you have linear momentum as well as angular momentum, which you represent as mvr. And even in the Bohr's model, you have written mvr is equal to nh by 2 pi. So this angular momentum property, you must have read in your physics textbook that when you curl your right hand, then the angular momentum is a vector property. So the curled fingers indicates the direction of the motion of circular motion, and your thumb tells you the direction of the angular momentum. Okay, so that's what is drawn here, not in the form of thumb. And this angular momentum is represented by symbol L, and it's one of the fundamental concept, because we have talked about in quantum mechanics rigid rotor and hydrogen atom, and in both the cases we found the circular motion. In rigid rotor also, if you remember, we reduced the problem of a diatomic molecule rotating in a plane to a one body problem by replacing with a reduced mass, and then we have shown that one particle is moving in a circle. Okay, so in case of hydrogen atom also, we have dealt with the both theta and phi equations in details. So this circular motion, which is whenever there is a circular motion, there is an associated angular momentum, which is a vector property, and it is given as L is equal to R into P. P is the linear momentum, so you can write mass into velocity. This angular momentum is important because when we talked about rigid rotor, I said you that in rigid rotor, when you reduce the problem from two body to one body problem, then you write the energy is equal to L squared divided by 2I. So this L, angular momentum, is actually responsible for the kinetic energy in rigid rotor. Okay, and this we have done already. So in this module, we will try to understand what is angular momentum, how this vectorially we can represent this different components of the angular momentum. Then we will talk about commutation relationships of the angular momentum. Then we will talk about ladder operators, and how ladder operators is used in quantum mechanics. And thereafter, I will talk to you one of the important property with which you are already aware is that whenever you write the magnetic quantum number and azimuthal quantum number, you restrict magnetic quantum number by saying that it will have 2L plus 1 value. So if L is equal to plus 2, you say it can have 5 different values of magnetic quantum number. 2L plus 1 will be 5 for plus 2. For 2 is the azimuthal quantum number. Then you say the magnetic quantum number is plus 2, plus 1, 0, minus 1, minus 2. Why it is restricted to 2L plus 1 values? Of how magnetic quantum number is restricted to this number 2L plus 1 values? So this we will see. We will see the different orientations of the component of angular momentum and how space quantization is done. I talked about a little bit in the rigid rotor also, when I talked about the importance of the phi function. We will talk about those in details. Okay. After that, I will talk about that how this angular momentum, different angular momentum interact with each other. If you have angular momentum, if you have a multi-electron which is present, then each electron angular momentum or vital angular momentum will interact with each other. So that we will talk about. And then there is another angular momentum which is called a spin angular momentum. It's a purely quantum mechanical property. It's not so as I hope till date what you have learned is that our electrons moves in the orbit and electrons also spins on its axis, and so because of this spinning motion we have a spin angular momentum. But clarify your concept. A spinning motion or there is nothing like a spinning motion in electron. A spin motion is a direct, a spin of quantum number is a direct observation from the experiment. It's purely quantum mechanical concept, and a spinning has no counterpart in classical mechanics. So you cannot say that the earth rotates in the orbit and on the axis, so is the electron. Okay. There is no classical counterpart of a spin motion of electron. It's purely quantum mechanical concept. We will talk about the spin angular momentum also. And then we will see that in a multi-electron atom, if you have orbital angular momentum and a spin angular momentum, then they interact with each other. And when they interact with each other, they give rise to different quantum state, which is called spectroscopic terms. So how do we derive a spectrum? Let's see how much I can cover, but there's a very wide application of concept of angular momentum in quantum chemistry. So we will start with the very basics, with the definition of angular momentum, and gradually we will build on advanced concepts on these basics. Since many of the potential learners may not have done much of mathematics, so I will try to do from the very scratch the concept of angular momentum. Okay, so if you define angular momentum, and we talk about first the classical definition of angular momentum, and then we will go for quantum mechanical concepts. So classically a quantum angular momentum is given as L is equal to mvr, that you know. L is the symbol for angular momentum, and mass into velocity into radius, in which the radius in which circle the particle is moving, and this we can write as r into p. Since again linear momentum is also a vector quantity, so what you can do is that you can split into different components, the linear momentum and the angular momentum, and you can write for linear momentum ipx, jp, I, j and k are unit vector, at least this much I expect you to know. So ipx plus jpy plus kpz, we can write for p linear momentum, and for r I can write ix plus jy plus kz. So what is the angular momentum? Angular momentum is multiple of r and p, and so if you multiply r and p, what do you get? First you multiply I with I, and then you have xpx, then you multiply j with j, you have ypy, then you multiply k with k, and you have zpz. So all three terms in the red. Okay, why it is in red I will tell you. Then you have I multiplied by j, so I into j xpx, xpy, and then j into k will be ypz, k into I will be zpx, and j into I is equal to ypx, k into j will be zpy, and I into k will be xpz. Okay, so there altogether there will be 9 terms, 3 terms here, multiplied by this one, altogether 9 terms we have. Now in these 9 terms, this cross product of I and I, j and k and k is equal to 0. Okay, so what will happen? All these 3 terms which is in the red, I and I, j and k and k will go will be deleted because it becomes 0. Okay, so this also again one of the fundamental relation of the vector algebra, I into I, j into j and k into k is equal to 0, so we use this one. Okay, we are talking about cross product, so all these are vector quantities. Now the cross product of I into j, j into k and k into I is equal to this one. I into j is equal to k, j cross k is equal to I, k cross I is equal to j. And what about the reverse one? J into I, j cross I is minus k, k cross j is minus I, and I cross k is minus j. That's why I have written here I cross j and here j cross I. Look at this one. It is j cross I, it's I cross j. It is j cross k and it is k cross j. Then you have k cross a and then you have I cross k. So all these are different. Okay. So same way we got the 6 terms which you will have. Now if you look at this one, then you have only 6 terms. For L is equal to R into P, the remaining 6 terms are this one. In these 6 terms, I into j is equal to k, I cross j is equal to k, j cross k is equal to I, k cross I is equal to j cross I is equal to minus k cross j is equal to minus I, and I cross k is equal to minus j. Okay, so you have I term minus I term, j term minus j term, k term minus k term, so that you can combine I together, you combine j together, combine k together, and if you do that, your L becomes equal to I ypz minus zpy, ypz from here and zpy from here, ypz minus zpy. j zpx minus xpz, okay, and then k ypx k xpy minus ypx, k is equal to this one, xpy minus ypx, okay. So you have, what does it mean? It means that this L, angular momentum, can be split into three components, one multiplied by I, another multiplied by j, and the third multiplied by k. So, what are these? These are unit vectors in x, y, and z directions. So what you can say is that this L can be split into three components, Lx, Ly, and Lz. And before that, if you have this particular equation for the angular momentum, this was the equation for angular momentum, then we can write this angular momentum in the matrix form. And so the matrix form is I, j, and k, x, y, z, px, py, and pz. So if any one of you have not done the matrix, then it is what? Matrix are written as A11, A12, A13, A21, A22, A23, A31, A32, A33. This is one of the matrix. This is called 3 by 3 matrix. The concept of matrix, if you have not done, you should do it, because I said you in the very beginning that the language of quantum mechanics is mathematics, and all when I will start talking about Huckel molecular orbitals, then this matrix application you will see. So the some fundamental concepts of mathematics you will have to learn, okay, then only you will be able to do the quantum mechanics properly, okay. Now the value of this matrix, if you have to write, then what you will do, you write the first term, this one, A11, okay, and then you omit the row and the column, both you omit it. Now the remaining part is a 2 by 2 matrix, okay. So what you do is you take the A, multiply this one this way and this way, okay. So and subtract it, A22, A33 minus A32, A23. This will be the first term. Then then you take the second term, A12, A12 with a minus sign, and what you do is you take this one and you neglect this first row and neglect this column. Again you have 2 by 2 matrix, A21, A31, A23, A33. So from this, what you do, you can write A21, A33 minus A31, A23, okay. And then after writing this one, again you write the third term plus A13. So let me erase this one, and now you are taking A13. So neglect this column and this term and the first row, and again you have a 2 by 2 matrix. So it will be A21, A32 minus A31, A22. This will be the value of the matrix, okay. So if you look at these relationships, it's exactly similar to what is written here. I ypz minus zpy, j zpx minus xpz plus k xpy minus ypz. So you have two terms here minus something. So everywhere is within the bracket you have the two terms, and outside the bracket you have one term. So you can write the matrix for this particular equation. It's just, let me erase it because this is not a, I wanted to tell you that how to write the matrix. Okay. So if you write the matrix and matrix is already written there, and if you want to get the value, you see you will get the value. If you take I, then what is the term which should be there? It should be this multiplied by this one and this multiplied by this one. So ypz minus zpy. You have ypz minus zpy. Okay. So this goes for the first term. Then if you write for j, then you omit first row, you omit middle column, and what do you get? You get zpx minus xpz. Okay. And then you have plus k xpy, k you are taking, so xpy and ypx. So this you get. So in the matrix form, you can write this equation. You can write this equation in the matrix form like this one. Okay. This you will be doing time and again. Wherever you have simultaneous equations, then you can write them. If you have two simultaneous equations with two unknowns, say you have a1 x plus b1 like we will come across with this one, c1 is equal to h11 minus es11 plus c2 is equal to h12 minus es12 plus again c1 is equal to h21 minus es21 plus c2 is equal to h22 minus es22. Then this kind of equation you will get in the variation treatment in the future. So what are these equations? These equations are two equations with two unknowns, c1 and c2, and this again could be written as in the determinant form: h11 minus es11, h12 minus es12, h21 minus es21, and h22 minus es22, and this will be c1 and c2. This is equal to 0. So a linear equations can be written in the matrix form. Simultaneous equations can be written in the matrix form, and this will be doing time and again. So I would suggest all of you to do a little bit of mathematics for the determinant and matrices also. I talked about the polynomials and all those derivations, differentiation and integration you have done. Do some matrices also in order to understand this quantum chemistry. Okay. And you should be aware of that with the development of quantum chemistry, there was a simultaneous development which was called matrix mechanics. The only difference between the quantum chemistry which we are doing and the matrix mechanics is that this uses the differential calculus, and in matrix mechanics, matrix is used. Okay. The result obtained from both the matrix mechanics and the wave mechanics was same, and this is more easier mathematically, so we are doing wave mechanics. Okay. So please learn some determinant and matrices that will be useful in the future modules also. Okay. So this equation can be written in this form. Now, if you have written this form, then this was all cross product. You should know the dot product also. All dot product of ii, jj, and kk is equal to 1, and all ij, jk, ki, ji, kj, ik is equal to 0. Okay. So this you should just to make a differentiation between the cross product and the dot product. Okay. What we say is that we can represent this as Lx component, this as the Ly component, this as the Lz component. So we can say this as Lx, this as Ly, this as Lz component. Okay. Now L square is actually a dot product of L into L, and this L square is given as Lx square plus Ly square plus Lz square. L square is a scalar quantity as it is a dot product. Okay. So remember, L is a vector quantity, L square is a scalar quantity. Okay. It's a dot product. Okay. Having done this classical concepts and learned the Lx, Ly and Lz value, we will go for quantum description of angular momentum. Okay. If we talk about quantum mechanical concepts of angular momentum, what we have done is that you replace Px, Py and Pz in the last row of the matrix by linear momentum operator. That is, what is the linear momentum operator? For Px, you write h cross by I ddx or minus IH cross ddx, it's the same thing, okay, both are same thing. Then you have for Py you write h cross by I ddy and or minus IH cross ddy, and for Pz you write h cross I ddz is equal to minus IH cross ddz. Now see, in the earlier equations, what you have written in the matrix, you are writing Px, Py and Pz, okay. Now this we are going to replace by operators or linear momentum operators, okay, the last row. If you replace it, then what you get? H cross by I is everywhere, so del by del x, del by del y, del by del z you get. And if you get this way, then you can write Lx is equal to what? Y pz minus z py. Look at go back and see. Lx is equal to y pz minus z pz. It's very symmetrical also. First x, and then it will be a combination of y and z. Then if you want to y, write y, again after y you have z, so z and x will be the combination, okay. And after, if you write z, then again you go back to x and y, you see. For if you write Lx, then Lx you will write y, Lx will be y pz minus z py. If you are writing Lx, no x will come on the right hand side, only y and z will come. So Lx is equal to y pz and z py. So combination of after x y comes and after y z comes. So you can write it very easily. Ly, if you have to write, then again after Ly, after y z comes, so z, and now y will not come. So it will not be z dz, it will be z px. Sorry, it will be z px minus, again z you have already written, so the next in q will be, the second cycle will be x and pz. So it's very symmetrical, and you don't need to mug it up. It's very easy to write. If you write Lz, then the first thing which will come is x, so x py and then minus y px, okay. So these three components you can write very easily, and now you are replacing this in the angular momentum with the angular momentum operator. So the only difference between the classical and quantum is that now we have started talking about the operators, okay. So we put the operator there, and if you put the operator, then what you can write? Lx is equal to y pz minus z py, and so you can write h cross by I y del by del z minus z del by del y. And if you look at this one, pz operator is del by del z, py operator is del by del y. So you see, pz operator is del by del z, py operator is del by del y. So you write y was there already, and for pz you write del by del z. For pz you write del by del z, and for py you write del by del y. Okay. So this way you can write others also. Ly, if you have to write, Ly will be what? I have written there. From y you have to start with z. So z px minus x pz. Okay. And then it is very easy to write h cross by I, z will remain there, and for px you will write del by del x will remain there, minus x will remain there, and for pz you will write del by del z. And then you have Lz. So now these are operators. These are not angular momentum. These are angular momentum operators I am talking about. Okay. So all these are not angular momentum. This is the linear momentum operator. It's already written there. And this is angular momentum operator. Angular momentum operators, which we obtain from the classical mechanics. I said your operators you get from the classical concepts. Okay, the only operator which you have to remember when I was talking about postulates, I said you that you need to remember is the operator of x and px. Then if you want the operator for energy, you can obtain it. The energy is equal to p square by 2m. So you put the operator of momentum and you square it and divide it by 2m, you will get the operator for energy. Okay. So angular momentum operators we obtained from the classical concepts. Okay. In the quantum mechanics, you get the operator for Lx, Ly, and Nz. Okay. So now, when we talk about the circular motion, I started talking about rigid rotor, and in rigid rotor, what we did, the first thing which we did is we converted Schrodinger wave equation to a spherical polar coordinates. Okay, and the same equation of in the spherical polar coordinates we used in the hydrogen atom also. Okay, so the operators which we have defined for Lx, Ly, and Lz is in the Cartesian coordinate, and this must be converted into polar coordinates because we are using the concept of angular momentum is for the circular motion, and for circular motion you will have the wave function in terms of theta and phi. Okay, so when you convert this, I have written directly the equations. It comes out to be I h cross minus sine phi del by del theta minus cot theta cos phi divided by multiplied by del phi. Then for Ly you have minus I h cross minus cos phi del by del theta minus cot theta sin phi and del by del phi. It's very similar to this one. Instead of sine you have cos here, and instead of cos you have sine here. Okay. In case of Lz, what you have x py, so it will be h cross by I x del by y minus y del by del x, and the operator for this Lz is minus I h cross del by del phi. So you see this particular quantity operator for Lz component of the momentum is very similar to the minus I h cross ddx. That's a linear momentum operator. Lx and Ly are not similar, but Lz operator is very similar to the linear momentum operator. Okay. Lz and Pz operators are very similar, like Pq if you write, it's minus I h cross. Q means Q could be Y, Q could be Z. So, but Q is equal to Z. Okay. So, Pz will be what? Pz will be minus I h cross del by del Z. So, if I remove this x and I write Z. Okay. So, very similar equations you have for the Lz component of the angular momentum. And what is the formula for the total orbital angular momentum in spherical polar coordinates? For total orbital angular momentum, the relationship is minus h cross square 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square. If you remember, this was the part of the equation for for Schrodinger wave equation in spherical polar coordinates. Okay, what you write is 1 by r square del by del r square del psi by del r plus 1 by r square sin theta del by del theta sin theta del psi by del theta plus 1 by r square sin square theta del square by del phi square. This was your del square psi value plus 8 pi square m by h square. That was the Schrodinger equation. So your Laplacian operator converted to spherical polar coordinates have three terms. The first term is 1 by r square del by del r square del psi by del r. The second term is plus 1 by r square sin theta del by del theta sin theta del psi by del theta. The third term were 1 by r square sin square theta del square psi by del phi square. Del square psi by del phi square. So here you have only r term. If you remember, just a quick recap. Here you have r and theta term, and in this equation you have all r, theta and phi terms in this part, the third term. Okay. And if you look at this equation and see what is this, 1 by sine theta, del by del theta, sine theta, del by del theta. So it is this part. From the second part, you have 1 by sine theta, del by del theta, sine theta, del by del theta. And the last part is 1 by r square sine square theta del square psi by del phi square. So remove r square and it is this part. This part you get from the third part, and this part you get from the second part. Okay. So this way we can convert all the relationship operators of Lx, Ly and Lz and L square into spherical polar coordinates. So these are the basic fundamental relationships for converting Px, Py, Pz equation into Lx, Ly, Lz and L square equation. Okay, we just got the relationship now. Okay. Now what will we do? We will try to evaluate the values of Lz and L square. Okay. But since the module will be a little longer, so this we will be doing in the next module. Okay. Thank you.